Okay, so we're now on to our last lesson. I know you all are sad, on inference for slope, plus a little bit of review of other things. So to study the relationship between calories and fat in pizza, slices of 14 randomly selected major brand pizzas are chemically analyzed. The computer printout for the regression is right here, and they want to know what is measured by S equals 1.27515. So if you did your notes, hopefully you did, you can see that the S, actually should just, S is the standard deviation of the residuals. So don't mix it up with S of X. We're talking about X. S, sorry, not X, S. So that's the standard deviation of the residuals. In other words, the variability in the residuals. Number 2, can dress size be predicted from a woman's height? In a random sample of 20 female high school students, dress size versus height gives the following regression results. Is there statistical evidence of a linear relationship between dress size and height? So what we look at, luckily, there's like almost nothing to do. It gives you the p-value in the right column. Now we want the p-value for the slope, not the y-intercept. So the slope is the one that goes with the variable height, and the p-value is 0.065. Well, so 0.065, first of all, they asked on B, it's not 0.128, it's 0.065, right? And so we know it's not no, because both of these don't have anything to do with the p-value there, all right? And so it must be yes for some. So let's see. We can see there's evidence at the 10% significance level, but not at the 5%. So that looks true. Let's double check. P-value of 0.065 is lower than an alpha of 10% or 0.10. So that means it would be significant at the 10% significance level, right? But at 0.05, it's greater than 0.05. So we would fail to reject at the 5% significance level. So the correct answer is E. Number 3, suppose the correlation between two variables is negative 0.57. If each of the y-scores is multiplied by negative 1, which of the following is true about the new scatter plot? So the slope is initially negative, whoops, and flipping it, let me go ahead and do my drawings. There you go. So it's initially negative, but multiplying every y value by negative 1 is like flipping the graph. So I just literally flipped it, and you can see that the slope now becomes positive. So the correlation should not change in magnitude. It should stay the same. So the correct answer is B. Number 4, a pharmaceutical company is interested in the association between advertising expenditures and sales for various over-the-counter products. A sales associate collects data on 9 products, looking at sales in thousands of dollars versus advertising expenditures in thousands of dollars. The results of the regression analysis are shown below. So I did notice my 7 degrees of freedom. I know I'm going to have to calculate an interval, and you can see that it's in the form the plus or minus. So I'm going to go ahead and pull this. This is straight out of your notes. Plus, it's your slope estimate, plus or minus your critical value, times your standard error for your slope. All right. So the slope actually is 12.633. So we can see that it's not C, D, or E. The slopes there are too high. So now we're just trying to figure out if it's A or B. Now, I do notice there's a standard error, which confirms, so see that matches 0.378, 0.378. So the next part I have to find is the critical value. So T star is the inverse T area. We want a 90% confidence interval. So that 90% is the area in the center, but inverse T only does left area. So I have to add a 0.05. So let's go ahead and review how to do that on the calculator. Remember to find critical values for T. We hit second distribution, and then we look for inverse T, which is choice 4 here. And our area is 0.95. Remember, we took the 0.90 plus the, so that's the center, plus, I'll just write it out that way. You can do that in the calculator there. Our degrees of freedom, they told us it was 7, and then we calculate, and we get 1.8945, etc. So now that we have our inverse t, we can substitute all of our values. It's 12.633 plus or minus 1.895 times 0.378. Answer B. Which of the following best explains why we try to guard against confounding when designing experiments? So number one, confounding can lead to bias. Actually, bias is usually a result of sampling design. It's not really an issue of confounding. And it definitely doesn't conflict with randomization. We randomize to minimize confounding. Confounding can lead to uncertainty as to which variable is causing an effect. That is exactly true. That is the definition of confounding, is that there are other factors, and you're not sure if the ones you're measuring are really the cause. So that's why we have to randomize in experiments, is to minimize that effect. And then the other two, no, it doesn't make it any more difficult to separate subjects into treatment and control groups. As long as we randomize, we should be fine. And confounding has nothing to do with blinding. So the correct answer is C. Number 6, which of the following is a true statement about the correlation coefficient? So first one, it says a correlation of 0.3 means 30% of the points are highly correlated. Actually, the percent explained is from R squared, not R, which basically is what statement B is, right? So B is true. The square of the correlation measures the proportion of the Y variance that is predictable from a knowledge of X. Okay, C, perfect correlation, that is when the points lie exactly on a straight line, results in R equals 0. R equals 0 means there's no correlation. The points look like random scatter. D, multiplying every Y value by -1 leaves the correlation unchanged. Well, we just did that in problem 3, right? When we multiplied it by -1, it flips the graph, and it actually, so a positive slope becomes negative and a negative slope becomes positive. So it changes the sign on the correlation. So that one is false. And then finally, E, the unit of measurement for correlation is the Y unit per the X unit. There are actually no units for correlation. So B is the correct answer. Number 7, a television game has 3 payoffs with the following probabilities. What are the mean and standard deviation of the payoff variable? So if you look at your distribution, so probability distributions on the front of your math chart, this is a discrete random variable. And you can calculate means by taking your values and multiplying them by their probabilities. So it takes 0 times 0.7, 500 times 0.25, and 5,000 times 0.05, and I would get 375. But then there's another little equation to the right, and that is to calculate the standard deviation right here. That one's a bit more of a pain. So what we're going to do today, so I could do it. I could say 0 times 0.7, 0 minus 375, square it times 0.7. So I could do all of that, right? But there's a much easier way to do it on the calculator, and I will show you how to do that now. So let's go ahead and put in our outcomes in a list. So we hit Stat, then we hit Edit, and let me go ahead and clear this list. I can clear by just going up to the top, hitting the Clear button, and then Enter. So our 3 payoffs are 0, 500, and 5,000. And then we go put our frequencies in list 2. Can you switch the order? Sure you can, as long as you remember which is which. And so what we're going to do, now you're probably thinking, oh, we got 2 variables. No, we have 1 variable, which is the payoffs, and the list of its corresponding frequencies. Then we go do one var stats, stat calc, yes, 1 var stats, hit Enter. So I have list 1, but if I just do that, it's actually going to give me the wrong value, all right? You can see that doesn't make any sense. Well, I mean, maybe it does. But let's go put in 1 var stats, and let's put in the list of frequencies, and you're going to see this is going to change. To get the list, hit Second List, and we want list 2 for our frequencies, and then we can calculate. And so now you can see that my expected outcome matches what I calculated before. So I didn't have to calculate it, but it was a pretty easy calculation, and it helped me double check I was doing this correct. Interesting thing, when you put in one of these random variable distributions, S of X, they don't put a number there. They can tell you have the whole population because all your probabilities add up to 1. So it gives you a sigma. And here you can see that it's very close to 1083. Now, I don't know if you noticed, and here, I have that still. I don't know if you noticed, but see this line right here? It actually showed up when I left off the frequency list. So they will anticipate you forgetting to put in the frequencies, but our actual answer is B. Number 8. A survey of 1,000 Americans reveals that 525 believe that whales are an endangered animal. So 525 out of 1,000 Americans, and should have protection from the fishing industry. And a survey of 750 Japanese, 325 believe the whales are endangered and should be protected. To test at the 5% significance level whether or not the data are significant evidence that the proportion of Japanese who believe that whales need protection is less than the proportion of Americans with this belief, a student sets up the following. Their null hypothesis is that the proportion is 0.525 and that the alternate is less than 0.525, where P is the proportion of Japanese who believe that whales need protection. Which of the following is a true statement? Well, we need to set up a hypothesis for the differences, not just one proportion. So it's not A, it's not B, it's not two-sided. We're wondering if it's less. So C, it's not C. And we don't want to combine the proportions. What we're trying to do is do a difference or proportion. So we would say proportion of Japanese is, let's see, to test whether the is less than, I would say the proportion of Americans minus proportion of Japanese would be greater than 0. So it's really a two population difference in proportions hypothesis test. Number 9, an experiment is conducted to determine whether taking fish oil capsules or garlic capsules has more effect on cholesterol levels. In past studies, it was noted that daily exercise intensity, low, moderate, and high, is associated with cholesterol level, but average sleep length is not associated with cholesterol levels, so less than 5 to 8, or greater than 8 hours. This experiment should be done by, well, let's find out. Well, those who exercise more probably have a more healthy lifestyle and less cholesterol. In fact, they said there is an association. We don't have to worry about sleep because there's no association, so it's not going to be a confounding variable. But the daily exercise could be a confounding variable. So ideally, we would block, since we know it and we have identified it in advance, we can block for it. So we're going to block, we're going to run 3 small sub-experiments, grouping people by exercise intensity, and this is called blocking. Number 10, the weight of an aspirin, not aspirin tablet is 300 milligrams according to the bottle label. An FDA investigator weighs a simple random sample of 7 tablets, and he obtains the weights of 299, 300, 305, 302, 299, 301, and 303. And he runs a hypothesis test of the manufacturer's claim. Which of the following gives the p-value of the test? So first of all, let's make sure we understand what the hypotheses are. So we believe that the mean is 300, but we're wondering if it's not 300. Since I don't see less than or greater than, my alternate is different. I can also tell my degrees of freedom is just my sample size, which is 7 minus 1 is 6. So now we can see that it is either A or B. Technically, I don't have to calculate the test statistic, but I will, and I'll show you how to do all this in the calculator. Okay, so one thing I can do is I'm going to need to calculate average and standard deviation at a minimum, right? So I'm going to go ahead and put this data in a list. I'm going to go ahead and put it in list 3. And let me show you something. You have to be careful when you're using a different list than list 1. All right, 301, 303. And let's see, so this shows I have 8 data points. Well, I'm on the 8th data point, so I have all 7 entered. That's good. And then you could say, well, let's go ahead and calculate the one variable statistic. So I already have this here with list 3. Make sure you have the right list, that you don't have any other frequencies. And remember, to switch list, you just hit this second button, and list, which is the stat button, we want list 3. So there we go. And calculate. And you can see that my mean is 301, And there's my standard deviation for the sample, which is what I would use if I was doing this by hand. But we're trying to save some time and do it using a test. So it's a t-test. And here's my hypothesized mean is 300, frequency is 1. So if I just go through and hit calculate, right, you can see, oh, hold on, my t-test, my average is wrong. So I kind of did that on purpose, by the way. Stat test. Make sure if you do that, you also have to change the list here. It's running list 1. So be careful with using a different list than list 1. Make sure you go back and change it to the appropriate list. If you had calculated one of our stats and had remembered to do it, then it would be fine. So we have a t-value of 1.54, and we know n is 7, so our degrees of freedom is 6. And there's our p-value, 0.175. 0.1754. So here we go again. So my test statistic is 1.54. Now these all had the same test statistic, so that wasn't that big of a deal, right? But it's nice for you to see how it goes. So I'm still trying to choose between A and B. Well, what I need to do is look at that alternate hypothesis right there. It's a two-sided test, so that means I have to multiply whatever probability of being that test statistic and more extreme by 2. So my correct answer is B. Number 11, which of the following is not true with regard to contingency tables for chi-square tests for independence? So the categories are not numerical for either variable. That's correct. They're categorical, all right? Observed frequency should be whole numbers. Yes, please. We don't want to observe half people. Expected frequencies, on the other hand, can be any portion you want. So that's false. They don't have to be whole numbers. Expected frequencies in each cell should be at least 5. And to achieve this, one sometimes combines categories for one or the other or both of the variables. So I do discuss that in the notes if you did the notes. The expected frequency for any cell can be found by multiplying the row total by the column total and dividing by the sample size, which would be the grand total, and this is true. So the only false one is C. Number 12. This is a scatter plot with one point labeled X. Suppose you find the least squares regression line. Which of the following is a correct statement? X has the largest residual and absolute value of any point on the scatter plot. That is false, and I'm going to show it to you in a second. X is also not an influential point. Why? Because it's probably very close to the regression line. The regression line would be pretty flat on here. I would probably have a correlation of 0 for a linear relationship, right? And then the next one is, the residual would show a curved pattern. Well, yeah, it would, because I'd have like this large negative, and then it would, so we would just be plotting the differences here. So we would see something very much like a curved pattern in our residuals, all right? The association between the X and Y variables is very weak. Oops. Well, that's actually false. The correlation is weak, but the association, if I used a different equation other than a linear, it's actually quite strong. Please don't mix up correlation and association. If the X point were removed, the correlation would be 1. No, because I'm trying to do a line. This is false. So it's still very curvy. It would still be very close to 0. So the correct answer is C. The residual plot would show a curved pattern. Number 13. In comparing the life expectancies of 2 models of refrigerators, the average years before a complete breakdown of 10 Model A refrigerators is compared with that of 15 Model B refrigerators. The 90% confidence interval estimate of the difference is 6,12. Which of the following is the most reasonable conclusion? Well, first of all, we have our boilerplate. We are 90% confident that the interval blank to blank captures the parameter in context. So first of all, what are we doing? We're comparing, right? So we're looking at differences. We're not looking at the expectancy of each fridge or averaging them together. So E matches our boilerplate, and it's looking at the right thing. Number 14. A banking corporation advertises that 90% of the loan applications it receives are approved within 24 hours. In a random sample of 50 applications, what is the expected number of loan applications that will be turned down? So hopefully you recognize this as a binomial distribution, and there's our formula for the mean. Note this is approved, and the sample size is 50, and 90% are approved. But it asks what percent will be turned down. So I have to go 1 minus 0.90, which is 10, and when I substitute, I get that. Number 15, which of the following months has the least variability as measured by interquartile range? That is the width of the box. And the smallest box width is this one, right up on top, December. You can see everything else is about the same size.